In 1938, a fishing trawler off the coast of South Africa hauled up something impossible. A 5-foot fish with fleshy, lobed fins and a body plan science had declared extinct for 66 million years, the Coelacanth. Its discovery wasn't just surprising, it was the biological equivalent of finding a living Tyrannosaurus rex walking through a forest, and it forced a question nobody had thought to ask. What if evolution didn't work the same way everywhere? The deep ocean is where evolution goes to hit pause, not because the process is broken, but because it solves its environment so completely that change itself becomes unnecessary. Below 1,000 meters, in the crushing darkness and near freezing cold, creatures have remained almost unchanged for hundreds of millions of years. Ancient body plans that should have been replaced, optimized, upgraded, they're still here, still working and still winning. This is the story of the deep sea's living fossils, and why the rules of evolution rewrite themselves the deeper you go. On December 22, 1938, Marjorie Courtney Latimer, curator of a small museum in East London, South Africa, received a phone call from a local fisherman. He'd caught something strange. She arrived at the docks and sifted through the day's catch. Sharks, rays, the usual, until she saw it. A metallic bluefish, nearly 5 feet long, with fins like nothing she'd ever seen, thick. Muscular, lobed, not like the thin, ray-supported fins of modern fish, but more like stubby limbs. She sketched it, preserved what she could, and sent her drawings to J.L.B. Smith, a chemistry professor and ichthyologist. His reply was immediate and frantic. She'd found a coelacanth, a member of an ancient order of fish, Coelacanthiforms, that the fossil record declared extinct at the end of the Cretaceous, when the asteroid killed the dinosaurs. 66 million years of absence. And now, one was lying on a South African dock. Smith spent the next 14 years searching for a second specimen. In 1952, a fisherman in the Comoros Islands, off the coast of Mozambique, caught another, then another. It became clear, this wasn't a fluke. Coelacanths had been living in deep volcanic caves and rocky slopes the entire time, hidden between 100 and 700 meters below the surface. Perfectly camouflaged in an environment humans rarely visited, the fossil record hadn't lied. Coelacanths had nearly vanished. But one lineage, the deep water one, had found a refuge so stable, so unchanging, that it never needed to evolve. The body plan that worked 400 million years ago still worked in 1938, and it still works today. The deep sea begins where sunlight ends. Below 1,000 meters, you enter the aphotic zone. Aphotic meaning without light. No photons penetrate this far, no plants grow, no algae. The entire foundation of surface ecosystems, photosynthesis, doesn't exist here. Instead, the deep runs on leftovers. Marine snow, a slow, constant drift of organic debris from the lit world above. Dead plankton, fecal pellets, molted shells, scraps of decaying tissue. It falls like ash, taking weeks to reach the abyssal floor. It's low-quality fuel, but it's reliable. It never stops. And for creatures adapted to this rain of detritus, it's enough. Occasionally, the deep gets a windfall. A whale dies and sinks. A large fish carcass descends. These food falls can sustain entire scavenger communities for months, but they're unpredictable. The baseline is scarcity. The deep sea is an energy-starved system, and every calorie counts. Then there's the cold. The water temperature below 2,000 meters holds steady at 2 to 4 degrees Celsius, 35 to 39 degrees Fahrenheit. It doesn't fluctuate. There are no seasons, no warm currents mixing in from the tropics, just uniform, bone-numbing cold that slows every biochemical reaction in every living cell and the pressure. At 4,000 meters, the average depth of the abyssal plain, the water presses down at 400 atmospheres. That's the equivalent of 50 jumbo jets stacked on top of you, or a pickup truck balanced on your thumbnail. To survive, organisms must build bodies that can't be crushed. Most deep-sea fish lack swim bladders, the air-filled sacs that help surface fish control buoyancy. Air compresses. It collapses. So they either float neutrally, their tissues saturated with incompressible fluids, or they live on the bottom. But pressure doesn't just crush, it distorts. Proteins, the molecular machines that make life work, are held together by weak chemical bonds. High pressure warps those bonds, destabilizing the protein's shape and breaking its function. To counter this, deep-sea creatures produce piezolites, small molecules like trimethylamine N oxide, TMAO, that pack around their proteins, cushioning them, keeping them stable even under crushing force. This biochemical adaptation comes with a cost. Once a species evolves proteins that need piezolites and high pressure to function, it can't go back. Swimming upward into lower pressure would destabilize those same proteins. The fish would die. The deep sea isn't just a refuge, it's a trap. The fourth pillar is space. The deep ocean is the largest habitat on Earth by volume, and it's mostly empty. Populations are sparse. Individuals are isolated. There's no intense face-to-face competition for territory, or mates like you see in a coral reef or a kelp forest. And without competition, without the constant evolutionary arms race of predator versus prey, hunter versus hunted, one of the primary drivers of change vanishes. These four factors, darkness, cold, pressure, and isolation, combine to create the most stable environment on the planet. While ice ages came and went on the surface, while continents drifted and mountain ranges rose and fell, the deep remained the same. And in that sameness, evolution found nothing to push against. Evolution is usually framed as an arms race. Predators get faster, so prey evolves speed. Prey evolves armor, so predators evolve stronger jaws. Climates shift. Food sources disappear. New competitors arrive. Life adapts or dies. This is directional selection. Evolution pushed in a specific direction by a new pressure. But that only works when the environment is changing. When it's not, the pressure flips. In a stable environment, the species that thrives isn't the one that innovates. It's the one that's already perfect for the job. And once you're perfect, any mutation that changes you makes you worse. A goblin shark with a shorter snout has less sensory range. A coelacanth that swims faster burns energy it doesn't have. A hagfish that grows eyes in total darkness wastes resources on an organ it can't use. This is stabilizing selection. Natural selection doesn't stop working. It actively weeds out anything that deviates from the optimal design. The average body plan, the one that's been working for millions of years, becomes the only body plan that survives. Innovation is punished. Consistency is rewarded. It's not that evolution pauses because the machinery is broken. It pauses because the environment has removed every reason to change. The deep sea doesn't reward novelty. It rewards efficiency, patience, and above all, not wasting energy trying to fix what isn't broken. This is why the term living fossil is slightly misleading. These creatures aren't fossils. They're not frozen in time. Their DNA still mutates. Their genomes still accumulate changes. If you sequenced a coelacanth's DNA and compared it to a 100-million-year-old coelacanth fossil, if that were possible, you'd find differences, lots of them. But those differences don't show up in their bodies. The mutations that survive are the ones that don't change the morphology, the shape, the structure, the function, the ones that keep the blueprint intact. Scientists call this braiditely, from the Greek for slow rate. It's not zero evolution. It's evolution in the slowest lane possible, with stabilizing selection acting as a speed governor, ensuring nothing important ever changes. And because these species are so well adapted, so finely tuned to their niche, they often outlast everything else in their lineage. The coelacanth isn't just a species, it's the sole surviving member of an entire ancient order of fish. All its relatives, all the other branches of its family tree, went extinct long ago during periods of environmental upheaval. The coelacanth survived because it was already in the deep, already adapted to a place where upheaval never reached. The coelacanth's body is a 400-million-year-old blueprint. Its most famous feature, those thick, fleshy, lobed fins, aren't just unusual. They're protolimbs. Inside each fin is a bone structure, homologous to the bones in your arm, one bone connecting to the body, two bones branching from that, then a spray of smaller bones at the end. It's the same architecture that became the tetrapod limb, the legs and arms of amphibians, reptiles, birds, and mammals. 375 million years ago, a related group of lobe-finned fish called Tiktaalik used fins like these to haul themselves onto land. Those fish became the ancestors of every terrestrial vertebrate. The Coelacanth's ancestors didn't make that journey. They stayed in the water. And when the world changed, when mass extinctions wiped out most of their relatives, the lineage that survived was the one that had already retreated into the deep. The living Coelacanth has other ancient features. It lacks a true backbone. Instead of vertebrae, it has a notochord, a hollow, oil-filled tube that runs the length of its body. This is the precursor to a spine, the structure found in vertebrate embryos, including humans, before it's replaced by bone, as we develop. The Coelacanth never made that replacement. Its skull has an intracranial joint, a hinge in the middle that allows the upper half to tilt back, opening its mouth wider. This feature is found in some fossil fish, but has been lost in all other living vertebrates. Its snout contains a rostral organ, a cluster of electroreceptors that detect the faint electric fields generated by muscle contractions in prey. In total darkness, this is how it hunts. But the most striking thing about the Coelacanth isn't its anatomy, it's its life history. It grows slowly, it matures late, it reproduces rarely. Female coelacanths are ovoviviparous, meaning the eggs develop and hatch inside the mother's body. The gestation period is 5 years 5, the longest of any known vertebrate. The young are born live, already 30 to 40 centimeters long and fully independent. Coelacanths can live to be 100 years old. They don't reach sexual maturity until around age 50. This isn't just a slow life, it's a slow generational clock. Evolution works by testing mutations across generations. A fruit fly with a life cycle of about 10 days can produce 10,000 generations in a single year. A coelacanth with a 50-year generation time produces 10,000 generations in 500,000 years. That's the difference between evolution in the fast lane and evolution in the deep. The deep sea doesn't just slow metabolism and movement, it slows time itself. The number of evolutionary dice rolls per million years drops to a crawl, and in an environment that never changes, that slowness isn't a disadvantage. It's the natural consequence of a life lived in perfect equilibrium. The Goblin Shark is what happens when a design becomes so effective that 125 million years of natural selection can't find a single improvement. Its family, Mitsucarinidae, dates to the Cretaceous period. Fossils of closely related species, like Scapinorhynchus, show the same bizarre morphology, an elongated, paddle-like snout, and a jaw structure unlike anything else in the shark world. The modern Goblin Shark, Mitsucarina austoni, is the only surviving member of that family. It lives on deep continental slopes, between 200 and 1,300 meters, drifting through total darkness. The snout is its defining feature. Long, flattened, blade-like. It's not a weapon, it's a sensor array. The surface is covered with hundreds of ampullae of Lorenzini, gel-filled pores that can detect electrical fields as faint as a few nanovolts. Every muscle contraction, every heartbeat, every twitch of a fish or squid generates a microscopic electrical signal. In the pitch black, where sight is useless, the Goblin Shark hunts by electricity. Its body is soft, flabby, almost gelatinous. Its muscles are watery. Its skin is translucent pink because there's no pigment. Pigment requires energy, and in a world with no light, there's no reason to produce it. The shark is neutrally buoyant, meaning it doesn't sink or float. It hovers. It doesn't swim in the way a great white does, powering through the water with muscular thrusts. It drifts, silently, slowly, scanning. And then there are the jaws. Most sharks have jaws fused to their skull. The Goblin Shark's jaws are held in place by elastic ligaments. When prey is detected, a squid, a fish, a crustacean, the shark doesn't lunge. It doesn't chase. It shoots its jaw complex forward. The entire upper and lower jaw protrudes from the skull, extending outward at 3.1 meters per second, fast enough to snatch prey before it can react. The jaws clamp shut, then retract, pulling the prey back into the mouth. This is called slingshot feeding, and it's one of the most efficient predation strategies in the deep sea. The shark expends almost no energy. It doesn't need speed. It doesn't need strength. It drifts, senses, strikes, retracts, repeat. And because this design is so effective, stabilizing selection has locked it in place. A mutation that shortens the snout reduces sensory range. A mutation that makes the shark more muscular, more active, requires more food the deep sea doesn't provide. A mutation that fuses the jaws to the skull, like in other sharks, means the goblin shark would have to lunge and chase, burning calories it can't afford to lose. The ancient design is already a perfect 10 out of 10 for the job. There's no mutation, no variation that improves it. So it hasn't changed. For 125 million years, the goblin shark has been drifting through the dark, slingshot jaws at the ready, a living monument to the power of stabilizing selection. The hagfish is older than fish. It's a craniate. It has a skull, but it has no backbone, no vertebrae, just a notochord, a flexible rod of cartilage running down its body. It has no jaws. Instead, it has 2 pairs of rasping keratinous plates on a muscular tongue that it uses to tear at food. It's nearly blind. It navigates by touch, using sensitive barbels, fleshy tentacles, around its mouth to sense its environment. It can absorb oxygen directly through its skin. The hagfish's body plan was established 300 to 330 million years ago, in the Carboniferous period, before the first reptiles walked on land. And it hasn't changed because it doesn't need to. The hagfish is a scavenger. It lives on the soft, muddy floors of the abyssal plain, hunting for worms and polychaetes, but specializing in food falls, the carcasses of large animals that sink to the bottom whales. Sharks, large fish. When a carcass lands, the hagfish arrives. It doesn't bite chunks off the outside. It burrows into the carcass, wriggling through decomposing flesh, eating from the inside out. Its flexible, tube-like body is perfectly suited for this, and because it can absorb nutrients directly through its skin, it doesn't even need to ingest everything. It can simply soak in the surrounding decay. This niche, deep-sea scavenger, is permanent. Animals have been dying and sinking to the seafloor for hundreds of millions of years. The job never goes away. And because the hagfish was one of the first to evolve a body plan optimized for it, it's never faced serious competition. But its most famous feature isn't its feeding strategy. It's the slime. When threatened by a shark, a grouper, anything that tries to bite it, the hagfish releases a protein and mucus mixture from glands running along its body. The moment this mixture hits seawater, the proteins unravel. They trap water molecules, forming long, tangled fibers. In less than a second, the mixture expands into liters of thick, viscous slime. The slime clogs gills. It suffocates. A shark that bites a hagfish gets a mouthful of choking mucus, its gills clogged, its oxygen supply cut off. The shark has to abort the attack, flee to open water, try to clear its gills. The hagfish, meanwhile, ties itself into a sliding knot, scrapes the slime off its own body, and sneezes to clear its nasal passages. Then it continues on its way. This defense is so effective, so universally successful, that it hasn't been updated in 300 million years. Predators have come and gone. Entire orders of fish have risen and fallen. The hagfish's slime defense remains the same because nothing has found a way around it. The hagfish is the ultimate proof that in a stable environment, simplicity wins. No eyes, no jaws, no backbone, just a flexible body, a talent for eating the dead, and a defense so overkill it's made the hagfish functionally immortal. Fossils can show you what an animal looked like. They can show you the shape of its bones, the structure of its skull, the arrangement of its fins. But fossils can't tell you how fast an animal was evolving. For that, you need DNA. The molecular clock is a technique that measures the rate of genetic change. DNA mutates over time at a relatively predictable rate. By comparing the DNA sequences of 2 species, counting the number of differences, and factoring in what we know about mutation rates, scientists can estimate when those species shared a common ancestor. And, crucially, they can measure how fast or slow each lineage has been evolving. When scientists sequenced the Coelacanth's genome, they confirmed what the fossils had suggested. The Coelacanth is an ancient lineage, a basal fish that split from the line leading to lungfish and tetrapods hundreds of millions of ago. But the genome revealed something more. The Coelacanth has the slowest rate of protein coding evolution of any known vertebrate. This isn't an opinion. It's a measurable fact. The genes responsible for building the coelacanth's body, the ones that code for its proteins, its enzymes, its cellular machinery, are changing more slowly than the equivalent genes in any other vertebrate species. Slower than sharks, slower than tuna, slower than mice, slower than humans, slower than anything. This directly ties the coelacanth's slow lifestyle, its cold environment, its 5-year gestation, its 50-year maturity, its 100-year lifespan, to its morphological stasis. The long generation times mean fewer opportunities for mutations to be tested by natural selection. The cold slows metabolism, which slows cellular processes, which slows the rate at which errors accumulate during DNA replication. And stabilizing selection ensures that even when mutations do occur, the ones that survive are the ones that don't change the body plan. The Goblin Shark and Hagfish likely show similar patterns, though their genomes haven't been as thoroughly studied, but the principle is the same. In a stable, low-energy, cold environment with long generation times, the evolutionary clock doesn't just tick slowly, it barely moves at all. This is the smoking gun. The fossils tell us these animals look ancient. The genes tell us they are ancient, at the most fundamental level. Their DNA itself is evolving in slow motion, a direct consequence of the deep sea's unbroken constancy. The deep ocean is both a refuge and a prison. It's a refuge because it shields life from the catastrophes that reshape the surface world. When the asteroid struck 66 million years ago, vaporizing rock and igniting global firestorms, the deep sea didn't feel it. When ice ages locked continents under glaciers, the deep remained 2 to 4 degrees Celsius, unchanged. When volcanic eruptions choked the sky with ash, the deep stayed dark, because it's always dark. This stability allowed ancient lineages to survive. The coelacanth, once widespread in rivers and coastal shallows, was nearly wiped out during the Cretaceous extinction. But the deep water population, the one that had already adapted to the cold, the pressure, the darkness, survived. And because that environment never changed, that population never needed to evolve. It became a living museum, preserving a body plan from the Devonian while the world above was overrun by dinosaurs, then mammals, then humans. But the deep is also a cage. Once a species adapts to extreme pressure, to the biochemistry of pezolites and protein stabilization, it can't leave. Its entire physiology is tuned to function at 400 atmospheres. Swimming upward would kill it. The deep sea traps its inhabitants, locking them in an environment where change is not just unnecessary, it's lethal. And that's the deeper truth about these living fossils. They're not evolutionary failures. They're not primitive in the sense of being inferior or outdated. They're evolutionary endpoints, species that solve their environment so completely, so efficiently, that natural selection found nothing left to improve. Evolution doesn't have a goal. It doesn't aim for complexity or intelligence or progress. It aims for fit, for a match between organism and environment. On the chaotic surface, that often means constant innovation, constant arms races, constant change. In the stable deep, it means the opposite. It means locking in a design that works and defending it, generation after generation, against any mutation that tries to alter it. The hagfish, with its slime and its jawless mouth, is just as evolved as a human. It's just evolved for a different world, a world where simplicity, patience, and an unbeatable defense are the keys to survival. The Goblin Shark, drifting silently through the black with its slingshot jaws, is a masterpiece of low-energy predation. The Coelacanth, with its lobed fins and notochord spine, is a living window into the anatomy that gave rise to every land vertebrate, including us. The deep sea didn't break evolution. It revealed what evolution looks like when the environment stops changing. And the answer is, it looks like stasis. like ancient designs, perfectly preserved, outlasting empires of species that burned bright and fast on the surface before vanishing into extinction. The deep sea is evolution's vault, and the creatures inside it are proof that sometimes the first draft is the final draft.